The sum and difference formulas give us the ability to evaluate angles and get exact answers that we couldn't do before. So for example, 15 degrees, which we're about to do, is not on the unit circle, and the only answer we could have gotten initially would have been from our calculator, and it would have been a decimal that would have required rounding or truncating, and therefore it would have been an approximate answer. So we can now do sine of 15 degrees exactly. We can also do 75 degrees, for example. And those are just some of the others that you're going to be evaluating with these identities. So what you have to do first is you have to look at these identities, and in our classes anyway, we don't make you memorize them, but you do have to know how to read them and how to use them. And so I want you to notice that what the first identity says is if you want to evaluate cosine of one angle plus, and that's the top symbol right there, another angle, then what you're going to do is you're going to do cosine of the first angle times cosine of the second angle. And then since we use the top symbol here to add the angles, we're going to use the top symbol here to subtract the trig values. So what that means is that there's a sign change in this identity. If the angles get added, the trig values get subtracted. Okay, and so that means, of course, the reverse would then be true. If we subtracted the two angles, so we use the bottom symbol here, we would add the two trig values. And a lot of the time we'll just go ahead and separate those trig identities for you and write them as two separate identities, but you do need to know how to read them when they are in their combined form. And then what you would do is you would do the sine value of the two original angles. And for the sine identity, there is no sign change. If I want to do sine of one angle, and then I want to add, so top symbol again, another angle to it, I do the sine of the first angle times the cosine of the second, and then I still need to use the top symbol. So there's no sign change, because I'm going to add the trig values because I added the angles. And then I'm going to do cosine of the first angle times sine of the second, which seems very strange, but we're going to try it, okay? And we're not going to work it all the way out both ways. I just want to show you all the different ways you could combine to get 15 degrees. So for example, if I said do sine of 15 degrees, what you would do is you would figure out two angles from your unit circle that could add or subtract to make 15 degrees. So for example, you could do 60 degrees minus 45 degrees. You could do 45 degrees minus 30 degrees. I mean, there's lots of different angles you could do to do 15 degrees. You could do 150 minus 135 if you really wanted to do that. I just chose quadrant 1 angles so that I would have all positive numbers. So let's say that I evaluated this one, because this one will give us the same answer. Okay? So what I do is I'm going to call this angle A, and I'm going to call that angle B. And so what I'm doing is I'm doing sine of A minus B. That's what I'm doing. And so what I'm going to do is I'm going to take this identity. Let me erase it and clear it out so it's not so covered in arrows. I'm going to take this identity right here, and I'm going to plug in, everywhere I see an angle A, I'm going to plug in my 60 degrees, and everywhere I see an angle B, I'm going to plug in 45 degrees. So I would do sine of angle A, which was 60 degrees, cosine of angle B, which was the 45 degree. The sine identity, I'm using the bottom symbol because I'm subtracting my two angles, so I'm going to use the bottom symbol here. So I'm going to subtract the trig values, and then I do cosine of the first angle, which was 60 degrees again, times sine of the second angle, which was 45 degrees. And then I evaluate. Okay? Now sine of 60 degrees from your unit circle is square root of 3 over 2. And cosine of 45 degrees is square root of 2. over 2 minus cosine of 60 degrees is 1/2, and sine of 45 degrees is square root of 2 over 2. Okay, and so what we do now is just follow PEMDAS. We're simply going to multiply and subtract. So when I multiply this first pair of fractions together, I get square root of 6 over 4. Second pair of fractions multiply together and give me square root of 2 over 4. And I want to stop for just a split second. I want to point out what I did in class. If you've done these correctly, when you get to this step right here, you will already have a common denominator. Okay, so these identities are set up to be theoretically user-friendly. Okay, and even though they've got a common denominator, square root of 6 and square root of 2, they won't subtract from each other, because square roots won't add and subtract unless they're the same square root. So I'm just going to leave the numerator written as the square root of 6 minus the square root of 2. There's nothing else I can do with it, but it is over the common denominator of 4. And that's it. That's my exact answer. Can't be simplified, doesn't need to be simplified. And so I want to know if square root of 6 minus square root of 2 over 4 gives you the same answer as sine of 15 degrees in your calculator. So if you have a calculator, make sure it's in degree mode and do sine of 15 degrees. And what you get is you get approximately 0.2588. And that is definitely rounded. And then you do square root of 6 minus square root of 2 all over 4, and you see that you get the same thing. So yes, our exact answer is equal to the approximate answer. But our answer is better because it is exact. Okay, so that's the first type of problem we do with these identities, and they are unit circle problems. Technically, these are also unit circle problems. We're just going to use the identities in reverse. So if we look at the first example, what I've got is I've got cosine of one angle, I'm going to call that angle A, times cosine of a different angle, so I'll call that angle B, minus sine of, and then we have the same first angle again, so I'm going to call that angle A again, times sine of angle B, because there was that 10 degrees again. And I simply match it to an identity. Okay, and the identity that it matches is cosine of A plus B. And so once I've matched it to an identity, the angles were already plugged into the long side of the identity, so now I simply plug them into the short side. Angle A was 50 degrees, angle B was 10 degrees, and on the short side of the identity they add together and it becomes cosine of 60 degrees. And then you can actually evaluate it from the unit circle and you can get 1/2. Okay, so ideally I'd like you to pause it for just a second and I'd like you to try the next problem that's just like it, match it to an identity and see what it becomes. Okay, hopefully you paused it and you gave it a shot, and so hopefully what you figured out is that the identity that it matches is sine of A plus B, and the angle that they had plugged in for A was 5 pi 12ths and B was pi 12ths. And once they're on the short side of the identity they can add, and of course you get 6 pi 12ths initially, but that reduces down. And so 6 pi 12ths is pi halves, and sine of pi halves is 1. So both of those types of problems are unit circle problems. They can be evaluated from the unit circle either by taking what's on the short side and plugging it into the long side, or vice versa. Okay. Then technically the second type of problem is our picture drawing problem that we've done in every unit of trig so far. So want you to notice first what we are being asked to evaluate. We want to be evaluating cosine of angle A plus angle B. So I'm going to write out that identity because I need to know what it is that I need. So cosine of A plus B says that I need cosine of A, cosine of B, minus sine of A, sine of B. And if you look at what you were given in the problem, you were given sine of A and sine of B, but you were not given the cosine values, hence the need for a picture. Okay, so they have told us that angle A is in between 0 and pi halves. That puts it in quadrant 1. So just draw a random triangle in quadrant 1, label it A. And over here, we were told that the sine value for angle A was 4/5. So that means we know the opposite side is 4, and the hypotenuse is 5. And that means that the adjacent side is 3. And now I know everything I need to know about angle A. I don't need to know how big angle A is. Okay, and I never will know how big angle A is. And then angle B was in between pi halves and pi, so that puts it over here. So once again, draw a random triangle over here in quadrant 2. We know the sine value for angle B was 5/13, so we know the opposite side is 5, and the hypotenuse is 13. And that makes the adjacent side, makes it 12 units long, but remember we're going left now because we're in quadrant 2, so it makes it negative 12. And now once again I know everything I need to know about angle B. So now I can go ahead and I can evaluate everything that I need to evaluate. Cosine of angle A is adjacent over hypotenuse, so that's 3/5. Please, please, please do not let me see you write it like this, because what you're telling me here is that angle A is 3/5 radians, and we never knew what angle A was. We don't need to know how big angle A is. We know the cosine of angle A. We do not know angle A itself. So just keep in mind that once you've plugged these numbers in, the goal is that all you should have left is numbers. If you don't have just numbers left, you have made a mistake somewhere. And you need to go back and fix it, please. Okay, and then cosine of angle B. So I go to the picture for B, and the adjacent side is negative 12 over the hypotenuse, that is 13, and then my minus sign that was right there. And then sine of A and B, I could get them from the picture, but I was given them, so I'm just going to use what I was given. Sine of A was given as 4/5, and sine of B was given as 5/13. Now remember, once we've multiplied, we should have a common denominator, so I'm not going to reduce my fractions as I multiply, because otherwise they won't have a common denominator, and I'm going to have to turn around and give them right back their common denominator. So when I multiply the first pair of fractions together, I get negative 36 over 65. Multiply the second pair of fractions together and I get 20 over 65. And then I subtract the two fractions and I get negative 56 over 65. And that would be the cosine value for whatever angle resulted from taking angle A and adding it to angle B. The only way to check your answer here involves inverse trig, which means it's harder and messier to check your answer than it is to just trust your answer and your identities. Because what you'd have to do is you'd have to find angle A, which means you'd have to do inverse trig. You'd have to find angle B, which means not only would you have to do inverse trig, you'd then have to convert it to an answer in quadrant 2. Then you'd have to add the two angles together and figure out what angle you got, and then you'd have to do the cosine of that angle. So I would recommend you not check your answer. Trust the identities and trust your picture drawing trig, and you'll be good. Okay, the final two problems are the final type. They're both solving problems. And they're very similar to the second problem we did that had a part A and B to it. We can't solve this equation right now because the left side has, number one, two different trig functions in it, cosine and sine, but they're each also evaluating different angles. And so we can't solve it. So what we do is we match it to the short side of an identity. And the identity that has sine of A, I'll write it over here. We have sine of A, cosine of B, plus cosine of the same angle A, sine of B, is the identity sine of A plus B. And so what we're going to do is we're going to use that. We're going to take this whole left side right here and plug it into the short side of its identity. And so we would have sine of, angle A was x, and angle B was 2x, and it's equal to 1/2. So what the left side becomes then is, now that angle A and B can add with each other, it just becomes sine of 3x, and it's equal to 1/2. So now it just became an equation that we actually can solve. And we're going to solve it just by peeling the layers away. We're going to take the inverse sine of both sides, and that'll get rid of sine on this side and just leave the 3x. Now when I do the inverse sine of this side, remember that sometimes it's optional. We just said it was a good habit to get into, to write it as a general solution. This time it's not optional. You have to write, let me change colors real quick. You have to write this as a general solution, because this 3 right here in front of the x is going to triple your number of solutions and the frequency with which your solutions occur, which you won't catch if you don't do the general solutions. Okay, so we are solving in degrees. So the two angles that have a sine value of 1/2 are 30 degrees and 150 degrees. As general solutions, they would both be plus or minus 360n. So cycle around 360 degrees, and you'll come right back around to those two angles and generate additional answers. But now our final step is to get rid of this 3 out here. So I'm going to multiply the whole thing through by 1/3. That'll get rid of the 3 here and just leave x by itself. Then 1/3 times 30 gives me 10 degrees. And then 1/3 has to also distribute to the 360, so it does not take 360 degrees to cycle to your next answer. You cycle every 120 degrees to another answer. Same thing happens down here. 1/3 times 150 is 50. And 1/3 times 360 is 120. And now I can use those general solutions to generate all of my answers between 0 and 360. Okay, so I'm going to start with my 10 degrees. Add 120 and you get 130. Add 120 again and you get 250. Can't add 120 anymore because then you're up past 360. So then I go to my next general solution, starts at 50 degrees. Add 120 once and you get 170. Add 120 again and you get 290. And there's your answers. And I want to point out, we knew that we were going to have 3 times as many answers. Normally, inverse sine of 1/2 would normally only have 2 answers. We got 6, which is 3 times as many. Okay, and that was because of the 3 out in front of the x. So once again, I want you to pause it for just a second. I want you to try to solve this one. This one does not work out exactly the same way, but it's the same premise, the same, match it to an identity and it becomes an equation you can solve. So just take a second and pause it, and then I'll come back and work it really quickly. Okay, hopefully you paused it and you gave it a shot, and hopefully what you figured out is that the left side of this identity matches cosine of A, which in this case was the 30-degree angle, plus B, which is the x, and it's equal to 0. So now once again I'm down to a 2-step equation. I need to peel my layers and move everything away from x, so I'm going to do inverse cosine of both sides, and that will get rid of the cosine over here, and just leave the 30 degrees plus x. And I need to do inverse cosine of 0 over here. It's a good idea to write it as a general solution just because it is a good habit to get into, but this time I don't actually need it because I don't have, over here on the left, I don't have multiples of x as the other part of my equation. I'm just going to have one final step, which is to subtract. Okay, but you notice this one also did not have a domain, so I'm going to write it as a general solution because I don't know what domain I would be solving over. Okay, so the angles that have a cosine value of 0, fortunately they're equally spaced, so I can just write one general solution. I'm going to write it in degrees, and that is 90 degrees plus or minus 180n. And then my last step is just to subtract the 30 degrees. It combines with the 90 because they're both like terms. This 180 has an n attached to it, so it won't combine. And so my solution is x equals 60 degrees plus or minus 180n. And that's it. Okay? So that is the majority of what we're going to be doing with our sum and difference identities. We do have one final topic to cover with them later on in our semester.